Okay, hello everyone. Welcome to Deep Learning System Action Implementation. So today it's going to be an exciting lecture. So we're going to work together to go through implementations of hardware acceleration libraries. And we're going to use the knowledges we learned from the last two lectures to build up some of these implementation that we're going to use for our third homework. So to begin with, we do need to select Colab with the CUDA support. So what you need to do, so it's the browse tab is a bit on the top that you cannot see it, but you want to go ahead and select runtime and change the runtime tag to GPU. So in this case, I already do it, and you can find that I get NVIDIA T4. So we're going to work together to go through implementations of hardware acceleration libraries, and we're going to use the knowledges we learned from the last two lectures to build up some of these implementation that we're going to use for our third homework. So to begin with, we do need to select Colab with the CUDA support. So what you need to do, so it's the browse tab is a bit on the top that you cannot see it, but you want to go ahead and select runtime and change the runtime tag to GPU. So in this case, I already do it, and you can find that I get NVIDIA T4 GPU in this case, and we're going to use it for some of our examples. Then what you want to do is you want to run this code block. Specifically, if you run it for the first time, you want to uncomment this code block that allows you to clone a local copy of Needle. In this case, lecture 14's version comes with a set of library implementations that allow it. And then you want to go ahead and do pip install pybind 11 that gives you a version of pybind in this case. So once we have that, we can go ahead and build a Needle CUDA library. In this case, the Needle CUDA library contains, so we want to be able to have a CMake file that allows you to go ahead and build the relevant library in here. So after we have that, we should be able to set the environment variable here, and then we will be able to use that to build our end-to-end neural network library. Okay. So while we are building, one of the things that we can do is let's start to take a look at the new code base that we have and compare, what's the difference between this code base and previous ones. If we look at this, we can find that, of course, we have our old friends. We have our old friends, a Python file. In this case, let's see. So of course, we will get our old friends that contains a set of Python files that we have, like Python here, CMake list, and a few other cases, right? Besides this, we also have, we also have a source file folder that contains two additional source files that correspond to the CUDA implementation that we had in here. And finally, I think the additional thing that we get is this C++ CUDA file along with a new folder. If you go to Needle, there's a new folder called backend ND array. And this is a folder that contains the implementations of the new ND array backend that tries to replace the original NumPy backend. So the main goal of this lecture is to help us to create acceleration library called ND array, and so that we do not need to deal with so we do not need to so that we do not need to use NumPy as a backend anymore. The result, actually, a lot of our today's content do not have things to do with Needle.tensor. And we'll focus on the backend ND array implementation in here. And after we build up this array library, we can then use it to power some of the backend array computations in Needle. Okay, and there are other files that comes along that you don't have to necessarily take a look. So I would certainly recommend you take a look at all the implementations in the backend ND array folder and the implementations on the source folder as well. We provide you a CMake list and a make file that helps you to build a library. So if you're interested, you're more than welcome to take a look. But it's not required that you have to go and look through every file in there. Okay. So first of all, we want to be able to create a backend ND array. In this case, what you can do is you can do from Needle import backend ND array as ND, and we will be able to create ND arrays. For example, I could do like x equals ND array 1, 2, 3, or I could do x equals ND array 1, 2, 3, but the device equals CUDA. In this case, you can go ahead and check the device is indeed CUDA, and if you try to read the content, it's now going to give you ND array 1, 2, 3. So actually, this is the first time we ever created a GPU array, even though if you may have not noticed it. There are a lot of like interesting things that are going on when we are starting to build this kind of implementation. Like for example, while we are doing ND array creation, we are copy data from our CPU memory NumPy onto a device memory, and then we are printing out all the contents that comes with the values. So of course, besides creating an ND array, we can also go ahead and do some arithmetics. For example, I could do y equals x plus 1. In this case, actually, it's a scalar, and this is actually the first implementation of a CUDA kernel that allows you to be able to take CUDA data and being able to do arithmetics on top, such as and this is like element-wise add. We can also do more like a tensor plus tensor. In this case, this is double the value. Of course, so on one hand, so that's kind of like a brief introduction of the ND array, what we can do with ND array. Now, let's take a look and dig deeper into what are the necessary elements we use to build up this ND array implementation. So in that case, we want to be able to take a look at the ndarray.py data structure in backend ND array, and then let's go through the code in here. So before I introduce it, one of the things that I would like everybody to step back and think about is how would you implement an ND array data structure? On one hand, we know that in most of the cases, the data structure that we have, right, most of the CPU memories and GPU memories allows you to have a flat array data structure that allows you to have, you can do a CUDA malloc to allocate a continuous region of memory. And one of the key things we want to do is we want to be able to turn that one-dimensional flat memory onto a multi-dimensional. That's exactly what ND array is doing here. So if you the main data structure of ND array is this ND array class, and this ND array class contains a few key fields. So you can find the key fields in this init file in here. You can find that it contains shape, strides, offset, device, and handle. So in this case, actually, all the fields, including shape, strides, offset, and device, are in Python. For example, shape is going to be a Python tuple. Strides is also going to be a Python tuple. Offset is going to be a Python integer. Device is going to be a data structure called backend device. The only thing that actually are dependent on some of the C++ file is this handle. And this handle file corresponds to a one-dimensional array, that pointer that we're going to look at. Okay, so effectively, in order to represent an n-dimensional array, what we want to do is we try to take a one-dimensional array handle, and then we are going to add additional fields such as shape, strides, offset, and device that represent a particular ND array. So now you might be a bit confused, right? So what does it mean to have a handle that's one-dimensional? So one of the things we can do is let's take a look and trace what happens. So in the code that we had in here, we used to do things like y equals x plus 1. So one of the questions we want to ask is, what happens when we do y equals x plus 1? What are the necessary functions and implementation that it goes through to implement that? Okay, so let's trace through what happens when we do like a GPU executions. So first of all, when we do x.ndarray 1, 2, 3, the first thing that we want to do is we want to be able to create a create a ND array, and in this case, the device is in CUDA. So in this case, if you look at the initialization function in here, the initialization function tries to goes into this one that says, if I'm trying to creating from NumPy array, actually in this case, it is something, it's not exactly a NumPy array, but we want to be able to, it's creating that one, right? So it's creating an ND array, a NumPy ND array, okay? And then it goes into an initialization function called array.device.from NumPy, okay? And by passing in the data content, so in this case, it first is called self.make to create an array data structure, and it then calls from NumPy by passing the NumPy data and array handle. Okay, so depending on what it is the corresponding device backend, actually the self.make function from NumPy actually dispatches to different execution modes. So let's take a look at some of them. Let me see. If you look at the initialize, so if you look at the make function in here, you can find that in the make function, it takes in shape strides, device, and handle. And if handle is none, what it will do is we'll try to call array.device.array by passing in a size field. So effectively, the underlying device backend will try to build an array function that try to return the array of the corresponding size. And the device.array function is being implemented by some of the arrays, some of the device. So in this case, the device goes into this backend device. It goes into this backend device class, and the backend device contains a module. So the module actually corresponds to the implementation. So when we are trying to do, device.array, actually it goes into this getAttr function, and then goes into self.mod.array in this case. And you can find that, for example, for CUDA, it goes into NDArray backend CUDA module. We also have a NumPy implementation actually that backs this particular computation specifically through NumPy. And we also have a CPU implementation. So now let's take a look at what happens when we call device.array. Okay? So there are different implementations. For example, in the NumPy backend, this is the array implementation. Effectively, what it tries to do is it tries to give a size and try to allocate array using floating point. So to make things simple, actually our array libraries only assumes the data type equals floating point. So you don't have to implement the other parts. Okay, so you can find that the array constructor effectively is creating an empty array. Remember, there's also a from NumPy function that copies A, which is the input NumPy data, onto the corresponding handle. In this case, just try to copy the array content onto this. So this is the implementation of a NumPy backend. Now let's take a look at implementation of a CPU backend for a bit. So it's another implementation, right? If you look at array constructor, this is a pipeline module that exposes several implementations. So if you look at array in here, what we try to do is we try to simply call the initializer of this aligned array data structure. So when we call array, what effectively it does is we'll call this aligned array with a constructor size, and under the hood it will try to allocate a pointer of a corresponding element size and a corresponding alignment. So effectively, in a CPU implementation, when you call this NumPy CPU backend.array, they will create the aligned array on the CPU side. And the second thing is, well, you remember that there's a call onto from NumPy. Right? So when there's a from NumPy, effectively it becomes an array copy that copies the data from A, which is the input NumPy array, onto the pointer that's get allocated of the aligned array. So you can find that in the case of CPU, each of the handle field correspond to effectively this pointer to an aligned array in this case. There's also a case of GPU. In the case of GPU, the handle corresponds to a pointer to a CUDA array. where we are doing CUDA malloc to allocate the total number of elements in here. And when we are doing destructing, we are doing CUDA free to free the corresponding element. And we can find that there's an array function that constructs the corresponding that constructs the overall arrays, what we call the CUDA backend module.array. And then there's from NumPy function that effectively runs CUDA memory copy by taking the data A and from the NumPy and doing CUDA mem copy from host to device to the allocated NumPy to the allocated CUDA array pointer. So you can find that effectively when we are doing these initializers, kind of a lot of things happens, right? So let's come back to the NumPy part. So when we're doing initializers, the first thing that we're going to do is we're going to call self.make, and that's going to call into this self.mode.device.array that goes into either the CPU, NumPy, or CUDA backend that allocates the corresponding array. And then we're going to call from NumPy, which actually does a memory copy, right? That copies the data from other onto the corresponding array underscore handle, and the underscore handle correspond to the allocated array field that you use to be able to allocate the corresponding memory and copy the data onto it. Okay. So here is the overall implementation of this constructing. Then we want to come and see what happens when you call y equals x plus 1. So what happens when you do an arithmetic computation here? So one of the things that we do in arithmetic computations, first of all, it's going to dispatch to an overloaded operator. So let's see what is the overloaded operator in this case. So you can find that the overloaded operator in here is the add operator, right? And it's calls into element-wise scalar to this operator. And effectively what we try to do is we detect whether or not the other field is an ND array or a scalar. Okay. So if the other field is ND array, what you try to do is you will invoke an element-wise function. Otherwise, we'll invoke a scalar function. So in this case, you can find a scalar function is correspond to self.divide.scalar add. So effectively, it's invoking a scalar function by passing in three things. The first thing is the left-hand operator handle, right? The second thing is the other corresponding the other handles. In this case, in the scalar, it's just a scalar value, and then it's an output handle, right? The second thing you realize is that in the output element-wise scalar or add, it first calls NDArray.make. So in this case, if you don't pass in any handles, it's going to create a new, it's going to call the array allocation to create a new empty array of corresponding shape. And then this corresponding scalar function, element-wise function, is going to do the computation and fill out the corresponding output array elements by running through the computation. Okay. So if you go ahead and look at the GPU implementation of scalar add, you'll find that there is a scalar add function in here that corresponds to scalar add function, right, defined in C++. So if you scroll up on the scalar add, let's see, you can find that this corresponds to the scalar add kernel, right? And you can find that in the scalar add kernel contains a few arguments. The first argument is a CUDA array that's being passed by the self.handle in the previous code. It's a scalar value as a second argument, and there's the output array field in there. And the scalar add kernel go ahead and invokes that kernel with the corresponding with the corresponding size. Okay. And then what you can find in here is that once you have a scalar add kernel, let's see. You will be able to go ahead and and this is the implementation of a scalar add. Effectively, you can find that this CUDA one-dimensional is an auxiliary function that will try to compute the corresponding launching size of grid and block, and we will be able to effectively divide things up through the number of threads, and we'll be able to launch this through this. And this is a typical CUDA implementation that we see in here. Now we can also go ahead and take a CPU implementation, which can be more simpler. So if you look at scalar add kernel function in here, let's correspond to a scalar add function in here that contains the left hand input, the values that are being added, and output that that gives you a sequence of that gives you the output content that you want to store into. And one of the things you'll notice that in all those cases, when we're doing arithmetic computations, we're explicitly allocating the input and output array. And then we're going to iterate over those iterator domains by taking the input, doing the additions, and writing that onto the output component in here. Okay. So we have the scalar add implementations, and one of the things you realize that is that in almost all the cases, a common pattern is we are going to allocate the output and then run the computation. Another thing that you might notice is that when we are passing in the handle, which is the array, right? There's always a call for compact, and this is because when we are representing the array in a multi-dimensional fashion, there's this field called strides and offset, which means that in certain cases, for example, if one trying to do additions of two-dimensional matrix, and depending on where the matrix comes from, directly passing the one-dimensional handle may not be right. So this is something that we can also come back in the next part, and you will see a bit more of why this is the case. Okay. So we have go through the key data structures of backend array and trace through GPU implementation. Now the final thing that we want to look at is what happens when you call y.numpy, right? Or what happens when you directly print out y that copies the data back to numpy. So in this case, you can find that when you call .numpy, let's see where the numpy operation is. And what it does is it directly call device.toNumpy, right? That copies the data onto NumPy device. And in this case, you will have self.handle, a shape, strides, and offset. And then let's take a look at CPU implementation of toNumpy. You can find that effectively it will try to copy the data onto the NumPy array by transforming the original strides to NumPy strides, and effectively create a NumPy array that correspond to a corresponding layout. And on GPU part, it could be a bit more slightly more complicated. In this case, you can find that it's going to first of all trying to copy the data from our original host pointer, right, onto the corresponding device by copying actually the entire array onto the corresponding device. And then it's going to create a NumPy stride array based on that particular part. Okay. So we have read through some of the code, right? So in this case, I would recommend everybody to go through and read the source.CUDA backend and CPU backend. These are like two backend implementations that implements both how do you do array allocations, deallocations through array and then deallocator. And they are represented by the underscore handle field, as well as the arithmetic implementation, such as the elements addition and Scala app. So we have already gone through the ND array field. So next part, let's go through and talk about strided computations. One thing you might notice is that there's this element called strides, right? And the shape and offset. So one question that we have is, why do we need strides? The reason being that depending on how do we specify the strides and shape and device, we could get different variants of an array. For example, imagine that we want to take this original ND array, which is a one-dimensional array that contains 6 elements. We want to reshape it. Let's say we want to reshape it to a 2x3 array. What you effectively need to do is that you do not have to really create a 2x3, a new array that is 2x3 and copy the data over. What you really have to do is you just need to be able to call ndarray.make by passing an explicit handle. So in this case, we are creating a shallow copy of the original ND array that's backed by the same underlying array memory. And then what we need to do is we just specify my shape is 2x3 and my strides equals 3x1. So effectively, we are still indexing to its original array, and my result zij is going to equal the array data I times 3 plus j, where 3 correspond to the first strides and j times 1 correspond to the second strides. So effectively, by specifying the shape field and strides field, you will get a different ND array that's reshaped. Not only will we be able to do reshape, we can do other operations. For example, one of the things we can try to do is, let's say, what if I want to slice it? Now we have this ND array of 0, 1, 2, 3, 4, 5, right? What if we want to just slice the second and third row? Okay, what can we do in here? So let's say we want to do a slicing operation. So let's say if we want to do b equals ndarray.make, and I want to do a slice. Okay. So because we want to slice, right? So the first question I want to ask is, what is the result of slice? Okay. We want to have a 2x2 matrix because, after slicing, it's a 2x2 matrix, right? In terms of strides, actually, we will keep the strides as it is. But then we want to be able to also specify the offset. So remember, the offset corresponds to the offset in an array that the first element corresponds to. So in this case, the first element is 1. And in this case, offset should equal 1 in this case. We go ahead and run it. You find indeed you get a slice of array, right? So in this case, you can find that this B array still is backed by the underlying handle that contains 6 elements, except that we are saying that my B array is shaped 2x2, and then Bij equals the data, the first offset, plus I times 3, which is the strides, plus j in here. And then that gives us a completely new array that's being sliced. Isn't that amazing in this case? We can also go ahead and do row slicing. So let's say I'm interested in getting the second row in here. So what do I do? If you want to do row slicing, you can find that we're going to get a 1 by 3 array in here. And then, of course, strides need to be the same, but the offset is going to correspond to the offset of 3. In this case, this offset equals 3. If we try that, you're going to get the second row in here. Right? So there are different ways we can go ahead and try to be able to create different values. And these different values correspond to, depending on how we are going to set the shape, strides, and so on, it's going to give us different things. Okay. Now we have tried slicing. The next thing we can try is we can try transposition. So let's say we want to take in this case z or x, and I want to be able to transpose it. So originally you can find z is 2 by 3. I want to transpose it to 3 by 2. In this case, if I want to do transposition, we know that the strides should also be transposed. If you try this one, you go ahead and run it, you can find that you get a transposed version. You get a transposed version that contains, 0, 3, 1, 4, and 2, 5. And that's exactly the transposition of our original array. And this is interesting in a sense that you can get a new version of an array by just swapping your strides and, of course, swapping your shape. So you can find that by manipulating the shape, strides, and offset field, we'll be able to get different views of the same original array that is being represented in a different way. Okay. So one last thing that I would like to mention is that we can also try to broadcast the original array. So in this case, let's assume that I want to broadcast on the first dimension, and that actually directly correspond to having a new shape. So I want to, originally it's a 2 by 3 tensor, and I want to try to make it 2 by 3 by 4. So I'm adding a new broadcasting dimension in the last dimension here. So if you want to do broadcasting, what you are trying to do is you are going to create a new array that contains 2 by 3 by 4 with also a strides field in here. And you can find that one of the key things here is because we are trying to broadcasting, we are trying to repeat that dimension, you simply set that strides equals 0. As a result, my index b, I, j, k is going to equal the data I times 3 plus j plus k times 0. Right? So effectively, the k index is not going to give you any offset. As a result, it's a result of broadcasting. So that's also another very useful thing if you want to be able to create an array that's being broadcasted on one dimension. And it's kind of amazing in a sense that we're creating a bigger array that's bigger than the total number of elements that we had on our original array, right? By just adding a dimension that contains 0 strides. Okay, so you can find that by running different ways of, by doing different things like different strides and shape, and we're going to get, and the offset, we're going to get different views of the arrays. And in the homework, of course, you are going to need to implement those different array transpositions and optimization. For example, you want to be able to take an array to swap certain x's. You want to be able to take an array and do array transposition, and you want to take an array, do slicing, and of course, take an array, do broadcasting. All those operations you don't have to implement it by running, by actually running and allocating a code and copy the data onto a new position. Instead, you are just going to create this new data structure that contains, contains the same underlying array but different shape and structure. Okay. So once we have these fields, the next thing that we want to consider is now we kind of have this multi-dimensional array. So you can find that we could have, for example, in this case, this sliced array that is kind of like correspond to one slice, depending on how you want to slice it, or we could have this transposed array. So in this case, this transposed array corresponds to an array that have a different iteration order. So if you read it out in one dimension, it should be 0, 3, 1, 4, 5, 2, 5, right? So imagine I'm going to add it. I'm going to take B and add it to, say, another, add it by 1, right? Or add it to another 2 by 3 tensor. In this case, if we directly pass in b.handle, you'll notice that when we do elements add, right, the underlying code of element-wise add directly takes in the flat handle. So let's go ahead. So you can find that, for example, in here, it simply takes in 2 arrays, A and B. It's going to iterate over that, and you're going to add each of element in here. But remember that if you are going to consider strides and offset, these things are not necessarily taken into consideration here, right? So when we're having an array that contains, for example, strides that does not correspond to a normal iterator order, or when you have an offset, then we're calling that this array is not being compacted. As a result, you cannot simply pass in this one-dimensional array and do the addition here. Another example would be, what if I want to do slicing? Say, in this case, I could try to make a 2 by 2 array by slicing the first element. So I'm getting a 4 by 4 array here. Right? Imagine I'm doing add 1 to this 4 by 4 array. Of course, we want to be able to pass in handle in here. But however, this handle corresponds to the original array that contains 6 elements. Right? So if we directly pass the original array onto scalar add, it's going to add all the 6 elements by that corresponding value. Say if I'm going to do things like z plus 1 in here, and if I'm going to directly pass in the original handle, then it's going to add all the elements besides the element that's getting sliced. So that's becoming a problem. So that is why that comes back to our previous discussions of why there's a compact function in the ND array implementation. So you can find that in this case, there's a compact function. And what compact try to do is it will check, first of all, if the array is compact. An array is compact if it's if offset is 0 and the strides directly correspond to the normal row major order that you will normally have. So effectively, if you flatten that array, it's correspond to the handle that you have. And so if the array is compact, this wouldn't do anything. So if you're allocating an array and not doing any transpositions on top, compact function is going to return the original array. On the other hand, if it's not compact, what it will try to do is it will try to make a new compacted array and call device.compact that tries to effectively take the original handle, right, that contains offside strides and shape, and trying to create a compacted version by really, in this case, we are copying the data onto the corresponding location. So the compact function is like a lazy function that try to check whether or not we are compact, and if not, we are trying to make it compact. The reason why we introduce things like strides and offset, and then in operation what you call compact function, it helps you to be able to lazily perform some more transformation. So you could imagine that I can have a case where I can do slides, transpositions, and broadcasting, for example, on multiple steps, right? And then at a certain time point, we need to call compact, so you are realizing that corresponding array. So in most of our implementations, for example, in the element-wise add, to keep things simple, we simply always call the compact function. So that makes our implementation simpler, right? So you just need to be able to always call compact function. So in this case, if you call the broadcast to or transposition or other operations, the compact function is going to give you a compacted version of the array. So effectively our implementation, you don't have to worry about whether or not I need to deal with the addition of an array that contains different strides and offset. On the other hand, we can create a specialized implementation from element-wise add that does not require a compactor. So we could have an implementation, for example, for 2-dimensional matrix we could have a two-dimensional iterator that iterate over I and j, create the add one, and then return the result. So it's really an implementation detail. A lot of the arithmetic libraries like NumPy and PyTorch do have operation modules that can take in those, slided array into consideration without having to deeply create a compactor version. And if you're interested, you're also more than welcome to implement that. On the other hand, when you use PyTorch in other cases, you might find that there are cases where they do explicitly call compact or contiguous. This is because on certain operations like matrix multiplication, it is useful to have a continuous memory access in a lot of cases. And as a result, some of operations like convolution and matrix multiplication, it's helpful to be able to call compact so that you get a contiguous implementation before you continue. So in our implementation, we will always encourage you to call compact to simplify your implementation. But you're also more than welcome to implement the arithmetic operations that work for non-compact memories, especially, for example, when you do a matrix multiplication, a lot of the existing implementation do allow you to have like a non-compacted iterators on at least one of the dimension. Okay, so that is how we do memory slicing and compacting. Now let's come back to example code. One of the things that we want to notice, we can do like a GPU acceleration. Right? So let's take a look at the GPU acceleration code in here. So in this GPU acceleration code, we can find that there are different definitions of coding here. Right? So for example, right now we define LMOS add, LMOS multiply, and let's see, what if I want to do, what if I want to add an operator? What if I want to add LMOS division, for example? So I will walk you through how we're going to do that. So first of all, we want to be able to define the two functions, LMOS division and scalar division, right? And then want to go ahead and define the corresponding kernels of those functions. Of course, because LMOS division is going to be very similar to LMOS add and multiply, I'm just going to copy the LMOS add and multiply kernels in here. And then I'm going to change the signature to LMOS division kernel. We know that the division is going to be like this. Similarly, say there's a scalar division kernel and a scalar division function here that allows us to perform scalar division. And we're going to invoke scalar division here and LMOS division. Okay. So now let's take a look at what we can do. So we can go ahead and call make, and we'll try to go ahead and build that function. And this is how we can do development, Colab environment, right? You can add a new function, and you can go ahead and try to build that new module. Okay. Now what we can do is we can go ahead and try to create an array, in this case, and then do x divided by 2. One thing you might find is that actually it caused that there's an error here, right? There's no LMOS division in this case. The reason is that although we build this array library, the current array module being imported in middle has not been freshed. So we kind of need to, in this case, if you want to do it in a Python notebook, you want to be able to go ahead and restart the environment in order to be able to do that. Let's not do that. Instead, what I'm going to do is I'm going to create a new test file. Let's rename it to be test. Okay, and we're going to directly edit this test file. Okay, So in this case, we're going to do from needle backend and array, and I'm going to do print x divided by 3. Okay. And what I can do is I can now go ahead and in the Colab environment, run Python test and try to run this. You can find that actually, whoa, the division result is modification. Seems that there's an error in my implementations. Let's come back and see what's going on. So let's go back to the CUDA code. Scala diff. Okay, this is not still modification. I'm going to save this. Call build again. And run this again. You can find, yeah, it gives you the right division result, right? So here's how we're going to implement this. And the reason why it works through this way is because every time we are invoking this Python test.py, it's going to give you a new Python session that helps you to be able to do things like, that effectively fresher import needle and allows you to do interactive debugging. So this is also a recommended way for you to develop some of the array libraries, and you can do the on-the-fly testing through this by creating new Python file. In certain cases, it is indeed a bit more complicated than IPython notebook, right? But however, this is a way that you can use to interactively use Colab as a development environment in the command line tool. So now, so far, we have only worked on backend and the array. One of the things I do want to notice is that we can build it and connect it back to a needle environment. For example, in this case, we are creating needle tensor as opposed to backend and the array tensor. And let's take a look at the current implementation. You'll find that in the current implementation, the only difference that we had in here is that instead of importing NumPy as array APIs, we're importing the backend and the array as array APIs. And we are importing all the implementation from a backend and the array library, and we are using array API .ND array. Okay. So effectively, what we're doing here is that instead of using NumPy, we're redirecting all the array computations to the array API. So similarly, on ops.py, you can find that there's import backend and the array as array API, and all our computations, like for example, computations of additions and so on, right? Almost all of them, correspond to this new ND array. And now in this case, it's no longer a NumPy ND array. Instead, it's the ND array implemented by the backend. So you're going to find that there's a compositional view in here, right? So we are first want to build up the underlying ND array library, and then in the needle part, we're just going to use that as a backend array that drives a lot of the tensor computations. Now this hierarchical view also allows us to be able to focus on implementing that lower level of the array perfectly, run through testing before we come back and really get a needle library that allows you to both do automatic differentiation and the underlying array computations. Okay, so we can also do a few more things, including doing things like gradient computation in other cases. I don't have time to run through all of them today, but you are more than welcome to go ahead and check it out. For example, in this case, we'll go and look at needle z.cache data. It's really backend ND array.ND array in this case. Okay, so that's the end of today's lecture. Thanks everybody for coming. Hopefully you enjoy the walkthrough of the new backend ND array library. And it's going to be used as a backbone for your homework 3. And hopefully everybody enjoys doing that. And after homework 3, we really get an almost complete version of needle library that contains both automatic differentiation, neural network implementations as well as the underlying endearing implementation that backs some of the GPU acceleration and the CPU acceleration code. Okay, so thanks folks. I will see you in the next lecture.